All right, good afternoon, everyone. Let's get started. Welcome to the EfficientML.ai. Today, we are going to introduce lecture 3 about pruning and sparsity to accelerate the inference of neural networks. So we'll have 2 lectures about pruning and sparsity. So today, we'll have the first lecture about that. So this is the overview of the part 1 of this lecture about efficient inference. We are going to cover 4 sections. Okay, we are going to start with talking about talking about pruning and sparsity, followed by quantization, like integer quantization, RP4, RP8, and also neural architecture search as a third part, how to design efficient neural architectures even before you compress them. And also we are going to conclude that by knowledge distillation, how to use a larger network to distill, to teach a smaller network, okay? So this is the agenda for the first part of this course about pruning. And we are going to conclude it by a real-world example, designing MCUNet and tiny engine to fit the neural network into a microcontroller by using all the techniques we learned in these 4 sections. So today we are going to jump into the first part, which is about pruning. So before jumping into pruning, let's start with some motivation and background. So when you first introduced this ML-Perf benchmark, which is the Olympic game for efficient AI computing for AI hardware. Okay, so ML-Perf basically tests the performance in latency and throughput given the particular accuracy on a suite of benchmarks. There are 2 divisions, the open division and the closed division. So in the closed division, you cannot change the neural network. You can only apply quantization. On the open division, you are free to change the neural network architecture and apply techniques such as pruning. So this is the latest benchmark from NVIDIA Blackwell platform, which was just a few weeks ago in late August. So in the closed division, the offline samples per second can reach 488 tokens per second. This is Llama 2 70B parameter large language model running on a single NVIDIA H200 GPU. In the open division, on the second column, the throughput increased to more than 11,000 tokens per second. This is a big improvement. And how is that achieved? And that is actually using the techniques we are going to learn in this lecture about pruning. So this technique applied 2 pruning techniques. One is depth pruning, reducing the number of layers from 80 to 32, followed by the width pruning, reducing the channel dimension from 28,000 to 14,000. And as a result, there's about 2.5x speed up running at a good accuracy. So hopefully that motivates the importance of pruning. And from the hardware perspective, why do we need pruning? So memory is very expensive. Computation is much cheaper. A memory movement is more than 2 orders of magnitude than the arithmetic operations. Like we have seen in the previous lecture, a 32-bit add takes less than 1 picojoule, while a 32-bit DRAM memory access is costing more than 600 picojoules. So data movement is much more expensive. So to make deep learning more efficient, we want to reduce the amount of memory, reduce the model size, reduce the activation size. Okay, so with that as the motivation, let's start with the agenda. We're going to start by introducing what is pruning, taking a dense neural network into a sparse neural network. In general, we can formulate pruning in this way. So we want to minimize the loss of the pruned model given the input X. Here, the L indicates, go back. So here the L indicates the objective function for the neural network training. We want to minimize this loss function when we have the pruned weights, WP, okay, subject to the number of non-zeros. Okay, the number of non-zeros should be smaller than a threshold. Okay, so we only want to have a limited amount of non-zero elements in the neural network to make it sparse, okay? And still minimize the loss. And then we are going to introduce the pruning granularity in coarse grain versus fine grain, and then the pruning criterion, which neuron, which synapses to remove, which neuron, which synapses to keep, followed by determining the pruning ratio. What is the redundancy? Can we reduce a lot? Can we reduce just a little bit? How do we select the pruning ratio while maximizing the amount of neural connections that is pruned and minimizing the loss of accuracy? And finally, we're going to talk about how to fine-tune, how to retrain the network so that we can recover the accuracy as the same as before pruning. Okay. So with that, let's start with the first part about introduction to pruning. So the pruning mechanism actually happens in human brain. So according to this study from Nature, a newborn child has about 2,500 synapses per neuron. Okay? And when he or she grows to 2 to 4 years old, this number surges to 15,000 synapses per neuron. It surges a lot. But during adolescence, this number didn't keep increasing, but started to decrease from 15,000 to only 7,000 synapses per neuron. Actually, the adolescence time is when we go to school, when we go to college. That's the time when we learn the most amount of knowledge through our lifetime. And pruning naturally happens in that time. And pruning also happens in artificial neural networks. Okay, so we can make neural networks smaller by removing those synapses and neurons that is redundant. So on the left-hand side is showing a dense neural network before pruning. Here it consists of 3 fully connected layers. Each layer is densely connected. On the right-hand side, we can do pruning on both the synapses and also on the neurons, so that not all the neurons is connected to each other. And how does this impact the accuracy? So I carried the experiment back in 2015. We first trained the neural network, and this is AlexNet, where we can achieve, this is the accuracy we can achieve. This is the baseline accuracy, and this is the distribution of the weight for a particular layer, roughly formulates a normal distribution. And then we can gradually prune the connections. So previously it was dense, now it becomes sparse. Okay? As we are getting sparser, we remove those small connections, those small weights. As a result, you can see the distribution, all the weights centered around 0, they disappeared. We remove them, meaning that we've zeroed them out. Okay, so the distribution changed. The small value disappeared. And you can see the more we prune, the less the accuracy. Okay? The more we prune, the less accuracy. The y-axis is the accuracy loss. Okay? The x-axis is the pruning ratio. The parameters prune away. On the right-hand side, you prune away all the parameters. You can expect the accuracy will drop to 0. And on the left-hand side here, we are starting from a 40% pruning ratio on the left. So this is quite unfortunate, right? People train these neural networks to get high accuracy, but suddenly due to pruning, you immediately reduce the accuracy by, here is like 1%, here is like 2%. That is too bad, right? Can we do better? We can actually train the remaining weights to recover the accuracy. Okay, so comparing this one versus after, we train the remaining weights that survived the pruning. Okay, train these weights that survived the pruning, and actually the curve moved to the upper right corner. Okay, what does it mean moving to the upper right corner? We can prune more parameters. We can prune more parameters, or we can achieve the higher accuracy given the same pruning ratio. Okay, and as a result, after the retraining, the weight distribution also shifted from this way to this way, becomes smoother. Okay, that's pretty good. Actually, we can prune away. Here is 90% of the parameters without hurting the accuracy here on AlexNet. That's pretty good. Can we do even better? How can we prune more without losing the accuracy? Actually, we can do this process iteratively, right? Not just do one iteration, but compare here and here. We can do another round of pruning, okay? So from the green curve to the red curve, we can prune even more. So about 90%, prune away 90% of the parameters without hurting the accuracy. So that debuts the whole process. You train the original network, you prune some of the weights according to the magnitude, and then you retrain the remaining weights that survive the pruning, and don't go too aggressive at each step. You want to go many smaller steps. Each step should be less aggressive so that you can push the boundary of this pruning process. As a result, these are the networks where, including AlexNet, VGG, GoogleNet, ResNet, SqueezeNet at that time, we can see AlexNet can be pruned from 61 million parameters to only 6 million parameters, about 9 times pruning ratio. And the max reduction is actually smaller. It's 3x. Okay? In the last lecture, we learned the difference between the number of parameters versus the number of max, how to calculate them for convolution layer, for FC layer, and also for attention layer. So they are not equal. For example, even networks that is super small, like SqueezeNet, which I and Kurt and Forrest designed in 2016, it's already pretty small to begin with. It has the same accuracy as AlexNet, but being 60 times smaller. AlexNet, 61 million parameters, SqueezeNet, only 1 million parameters. So we can still prune such a very small and compact model, okay? From 1 million parameter to only 0.38 million parameters. That's 3.2x reduction for the model size. Not only for such image tasks, but also for visual language tasks like caption, we can still also prune it. For example, the first image, given the caption, original caption is a basketball player in the white uniform is playing with the ball. Okay, it's indeed the case. And if you prune away 90% of the parameters, it says a basketball player in white uniform is playing with a basketball. It's pretty accurate. Second image, the baseline model says a brown dog is running through the grassy field versus prune 90%, a brown dog is running through a grassy area. Including the third one, riding a surfboard on a wave, a man in a white suit riding a wave on the beach, prune away 90%. What if we prune more, like pruning away 95%, be more aggressive? So on the third image, the original model, baseline model says a soccer player in red is running in the field, versus if you prune away 95%, it says a man in the red shirt and black and white black shirt is running through a field. It's getting drunk, right? So there is a limit how much you can prune, cannot prune too much. And we're going to later see a demo showing the process when we are doing the pruning from 70%, 80%, 90%, all the way to 99% until we break the model. And I highly recommend you try this experiment offline at home. We're going to give you the code for this IPython notebook. So in recent years, pruning and sparsity is getting quite popular. This whole domain started back in 1980s with the paper Optimal Brain Damage. And then throughout the years, it gradually increased until 2015, 2016, when I published this paper called Deep Compression, we show that these modern neural networks, given large-scale data set, large-scale GPU training, we can aggressively prune it. There's a lot of opportunity to optimize the hardware efficiency by looking through at the algorithm level, right? And then we can also design specialized accelerators like the EIE, the Efficient Inference Engine, to accelerate directly on a sparse and compressed model. In recent years, the number of publications per year is just surging very fast in recent years. And this has been adopted in industry, like pruning in industry. Left-hand side are the 3 papers I published. First 2 during my PhD and the last 2 during when I was at MIT about how to accelerate building specialized accelerators to accelerate matrix multiplication and different workload. And NVIDIA adopted sparsity in the GPUs. After the A100 GPU, NVIDIA introduced the 2 to 4 sparsity. We're going to introduce that soon. So turning a dense matrix into a sparse matrix and have about 2x theoretical speed up and about 1.5x measured speed up. And Xilinx, now part of AMD, also use the sparsity to optimize their models using this AI optimizer. It acquired previously my startup and built it into a software toolchain to prune the model and fine-tune the model. And as a result, you can get a faster inference. Okay, so let's go to the next chapter about how to determine the pruning granularity. Okay, in what pattern should we prune the neural network? So pruning can be performed at different granularities, can be very fine-grained or very coarse-grained. You can imagine there's a very big design space. So turning from this very dense 2D weight matrix, we can make it a pruned. The red one means it's preserved, and the white rectangles means it's pruned. Fine-grained pruning is most flexible, and we can prune any weights in any location. But the drawback, what is drawback here? It's hard to accelerate, right? For GPUs, different threads prefers to be doing the work in lockstep manner. Everything want to be parallelized, do the same thing, no branching, right? But there's a lot of irregularities, which is not hardware friendly. What is the advantage here? You have the most flexibility. You can prune any weight you want. Okay, so the pruning ratio is the highest using such fine-grained pruning. In contrast, we can also do coarse-grained pruning. Okay, so in this case, we are pruning the entire row. We are pruning the third row, the fourth row, and another row. We prune through 3 rows in the middle. Okay, what is good about that? We can condense it into a dense matrix and still apply dense matrix multiplication to do the arithmetic. Okay, so the good thing is about it's easy to accelerate. It's very structured. It's very regular. You can just apply the dense matrix kernels, but you can imagine this is less flexible. Okay, if you prune, the whole row has to be pruned, or the whole column has to be pruned, and the pruning ratio is much less compared with the previous example, the fine-grained pruning example. Okay, so let's talk about the pruning granularity, not just for the FC layer, but also for the convolution layer. Okay, in the convolution layer, there are 4 dimensions for the convolution kernel. CI is the number of input channels. CO is number of output channels. And we have KH and KW for the kernel's height and kernel width. And these 4 dimensions give us more choices, more degree of freedom to select the pruning granularity. So we start with the fine-grained pruning. In this notation, we have KH and KW equal to 3. It's a 3 by 3 kernel. And here we have 3 output channels. And here we have 2 input channels. So we rated the 4-dimensional convolution kernel and visualize that in this way. So this is the fine-grained pruning, pattern-based pruning, vector pruning, kernel level pruning, all the way to channel pruning. This is the whole landscape. And now let's dive deeper into each of them and talk about what is good about it, what is bad about it, what is the trade-off. Everything is about trade-off. So fine-grained pruning, okay, is irregular, but it's most flexible. You can have the highest pruning ratio if you're just targeting compressing the weight without worrying about acceleration or parallelism. This is the way to go. Okay, it has very flexible pruning indices, and you already have larger compression ratios since we can very flexibly find those redundant weights. For example, here we can compress it by up to like an order of magnitude for these different neural networks. It can also deliver speed up on specialized hardware. If you have the capability to design specialized hardware like EIE, the Efficient Inference Engine, which I published in ISCA 2016, You can do that, but it's not easily accelerated on off-the-shelf hardware. A second category, the pattern-based. Okay? So the prune kernel has some patterns. Okay? Like this is one pattern, you rotate it by 90 degrees, same pattern. These patterns are the same. Okay? So this is actually give you more regularity compared with the fine-grained pruning. One notable pattern is the N to M sparsity, for example, 2 to 4 sparsity. So start with a dense matrix on the left-hand side. We can prune it to a 2 to 4 sparse matrix. So give you 1 minute to take a look at the pattern. Anyone can tell me what is the pattern here on the right-hand side, the matrix. So what pattern do we see on the second 2 to 4 sparse matrix? Right, every row has 4 missing values, right. And actually, if you look deeper, like the first row, 4 missing values, and actually, this is due to every group of 4 elements, you must have at least 2 zeros. Okay, so 2 to 4 means out of 4 entries, at least 2 entries has to be 0. And that is the case for every group of 4 elements. And that's why we call it 2 to 4. So it's 50% sparsity. And how many bits do you need to indicate the location of the non-zero or the 0 element? You have 4 choices, therefore you need 2 bits to indicate where the non-zero, where the 0 are. Okay, so that is the metadata, the overhead you have to store. You have to store 2 bits for the index. So it really well maintained accuracy. So this is the test of accuracy across different benchmarks, like less than 50, exception, BERT, etc. Comparing the dense accuracy versus the sparse accuracy. You can see it's pretty much the same, 76.1, 76.2. The accuracy is pretty well maintained using this 2 to 4, roughly 50% sparsity ratio. Okay, so we can also do this channel level pruning. Okay, we omitted this middle 2 figures for it is following the similar principle. We are just getting more and more regular, but less and less degree of freedom. The extreme case is the channel pruning, where we are pruning away the entire channel. Okay, so the pro is that we can directly speed it up due to the reduced number of channels, leading to a neural network with a smaller number of channels. And it's still dense. You don't need any specialized hardware, just using CPUs, using whatever hardware you originally have, you can directly accelerate it. But the con is you can have a smaller compression ratio. For example, for convolution neural nets, like mobile net, you can prune away only about 30% of the parameters of mobile net. So here we are showing the neural network with 5 layers. We can prune the channels with different sparsity ratio across different layers. And there are 2 ways. One is to do uniform shrinking. So for all the layers, you apply exactly the same sparsity. In this case, 30% sparsity. But that is usually not as good as having a smarter way to figure out the redundancy and sparsity for each layer individually. Like on the right-hand side, we will later discuss how to find the optimal sparsity ratio to allocate to different layers. We are going to talk about sensitivity analysis in the next lecture. This also applies to recent large language models, where the convention in Llama 2 is that all the layers are repeating the same transformer building block, exactly the same number of channels across different layers. It's very homogeneous. It's very easy to partition, especially for model level model parallelism. Distribute the weight across multiple GPUs. But if you want to extract the inference efficiency to the extreme, different layer indeed may have different redundancy and sparsity ratio. And we don't necessarily have to keep the same amount of channel number across different layers. Usually sensitivity analysis help to analyze that. So we are going to talk about in lecture 2 of pruning. And this phenomenon is further demonstrated on this figure, comparing the uniform scaling for all the layers, just uniformly shrink it by the same percentage, prune away the same percentage for all the layers, versus using an optimal, a better optimized sparsity ratio search algorithm. Here is AMC, automatic model compression, to search that. And here is the latency versus the accuracy trade-off. The search approach have a lower latency and higher accuracy in this case. So the student did this work, was the TA for our class last year. His name is G. He joined OpenAI after graduation. This is his work. Okay. All right, so let's jump into the next part. How to determine the pruning criteria. There are so many weights in neural network. So which one do we keep? Which one do we prune away? What is the criteria for the weights, for the synapses, and for the neurons? So we are going to talk about this pruning criteria. Okay. Of course, we want to reduce those. We want to prune away those less important parameters so that we can maintain the accuracy or minimize the loss. For example, in this case, we have only 3 weights. 10x0 minus 8x1 minus plus 0.1 x2. I really want to show a very simple example for intuition, right? Give you some intuition which ones to select to prune. If out of these 3 weights, 10 minus 8, 0.1, if one weight has to be removed, you have the capacity to hold only 2 parameters. Which one should you remove intuitively? 0.1, right? Because it's smallest, likely to have the smallest impact. So that is actually the most simple, the very effective way to determining the pruning criteria. Just select the small ones, super easy. So the importance, we just use the magnitude of the weight to indicate the importance of the weight. If the importance is small, the magnitude is small, then we just remove it away, also called magnitude-based pruning. So we want to maintain the weights with large absolute value and prune the weights with very small absolute value. Okay, that is very simple heuristic, but turned out to be working super well in both academia and industry for so many years. In the example on the bottom, we have 4 weights. We find the L1 norm for each of them, and this is the L1 norm. And we keep the red, the largest, and remove the smallest. So this becomes the pruned weights. So just use the absolute value to determine the pruning criteria. Okay. What about for four-screen pruning? For example, if you want to prune away the whole row of this matrix, we can apply L1 norm or L2 norm. For example, here we start with L1 norm, magnitude-based pruning. So we find the L1 norm for the first row, which is 3 plus 2, which is 5. We also find the L1 norm of the second row, which is 6. Okay? And here we compare 5 is smaller than 6. So we are going to prune away 5 to L1 norm and only leave the second row unpruned. Similarly, we can also apply L2 norm. So this is the way to calculate L2 norm. It's very simple. I won't repeat it here. That is the very similar heuristic. Just use the magnitude, no matter if it is a tensor or if it is a just a single value. Okay, and in general, we can use the LP norm to determine the pruning criteria. We can also apply this scaling-based pruning technique. For example, here we have n filters from filter 0, filter 1, all the way to filter n-1. And we apply a scaling factor to associate each filter with a scaling factor. Okay, so here is the scaling factor associated with each channel. Like the first channel will be multiplied with 1.17. Second channel will be multiplied with 0.1. And that scaling factor is learnable. Okay, so that's learnable. You have one learnable parameter for the whole channel. So it's actually very parameter efficient. You only have n numbers to learn right here. And you want to minimize the scaling factor to try to push them to 0 so that we can easily prune them away. Like here, if the scaling factor is 0.1 compared with 1.17, this is pretty small. So likely we are going to remove the second filter, filter 1. Okay, so we can later sort the scaling factor and prune away the channels with a very small scaling factor. So originally, this was the number of filters, and we removed the channels with small scaling factor, and the neural network becomes something on the right-hand side. The filters and output channels with small scaling factor will be pruned. Question? Of course, there are many other heuristics we're also going to cover very soon. So this is the first heuristic, very simple, but there are more complicated ones. Let's talk about that. And to continue to talk about the scaling factor right here, the scaling factor can be reused from the batch normalization layer, which we learned from the previous lecture. For the batch normalization, you have one scaling factor per channel. Okay, you have one scaling factor per channel. That's exactly the scaling factor that is here. So you can reuse the same scaling factor from the batch normalization layer to simplify the calculation. What other heuristic do we have? Magnitude may not be the best one, right? It's hard to tell. Usually, it's hard to tell which is the best heuristic, depending on the data set, depending on the neural network. It's experimental stuff. But here, let me introduce the design space. So when you are doing such pruning tasks in the future, you at least know what is the way to think about it. What are the choices? There's never a conclusion which one is the best unless you try it. Second order based pruning. Okay, so let's apply the Taylor expansion to a pruned network. This is the pruned network versus the original network. Pruned network, you basically give a perturbation to the W to the weights of the delta W, which is equal to, this is the first order, second order, and the third order approximation. Okay, so we can remove the third order and beyond, and only keep the first and second order. The paper Optimal Brain Damage suggests that the last term is we can neglect them, and then the twinning has converged, so the gradient should be very close to 0. You already converged at the local minima, so first order you can neglect them. So only the second order term is there. A second order term has two parts. The error caused by deleting each parameter assumed to be independent. So the cross term can also be neglected. And as a result, we only have one term in the middle, which is the second order term. And we use that to determine whether this weight is important or not. Okay, so the importance is summarized in this way, where the H is the Hessian matrix. But the downside is that the Hessian matrix is difficult to compute. So we have to apply some approximation to compute, to estimate the Hessian matrix. Okay, so beyond the synapses, we can also prune the neurons. When we removing the neurons and removing the synapses, they are very highly related. So removing the neuron is equal to actually a very coarse-grained weight pruning. For example, in the linear layer right here, removing one neuron right here means we are removing all the weights associated with this output neuron, meaning that we are reducing one row in the weight matrix. Similarly, in a convolution layer, when we are removing some of the output channels, it also means we are removing the entire kernel corresponding to that channel. Okay, so let's talk about one way to determine which activation to remove. Using the percentage of zero based pruning. Okay, since ReLU will generate a lot of zeros. Okay, so here we have a batch of 2. This is batch 1. This is batch 2. And we have 3 channels, and each channel is 4 by 4. So there are two feature map batches. And we just calculate the average percentage of zeros in these 2 batches. So rather than using complicated math, let's just see that from a simple example. Okay, so there are 2 batches. What is the average percentage of zero of channel 0, channel 1, channel 3? For channel 1, here we have 5 zeros. Okay. And in the second image, we have 1, 2, 3, 4, 5, 6. We have 6 zeros. And how many elements do we have in total? 4 by 4, we have a batch of 2. So 2 times 4 is 4, 32. So this is the average percentage of zero for channel 0. Okay, and similarly, we can calculate that for channel 2. We have 5 zeros here, 7 zeros here. So average percentage of 0 is 12 divided by 32. And similarly, we can calculate for channel 2. And we compare them, and we are going to remove the channel with the largest amount of average percentage of zeros, since they are supposed to be redundant. And this is done by, rather than using a static way for measuring the weight. Okay, when we are pruning the weight, you don't have to run any input. You just statically look at the weight. But for the activations, right, you have to really run a few samples so that you can calculate the average percentage of zeros. Okay, so in this case, we run a batch size of 2, and then we calculate the statistics of these 2 samples so that we can calculate average percentage of zeros. All right, let's take a short break before jumping to the next method. All right, welcome back. Let's resume the lecture. So just now we talked about activation pruning, right? So a common question here is the tensor here is no longer the weight. Okay, this is the activation tensor. Those 6 matrices, those are the activations, not the weight. That's if I didn't explain that clearly before, now is the time to clarify. These are the activations, and we are trying to prune the activation channel. And we run through the network with 2 input examples. Therefore, we can get 2 categories. Okay, so this is the first. This is the first batch. This is the second batch. Okay, we run 2 samples. Both are activations, and we collect the statistics about these activations to perform activation pruning. All right. So next, regression-based pruning. So what is regression-based pruning? Usually, if you run the network end-to-end to calculate the loss, that could be pretty expensive. For example, if you want to prune llama and you want to use the last loss as the end loss as your supervision when you are doing the retraining, that could be super expensive. As opposed to that, we can minimize the reconstruction error of the corresponding layer. Okay, to layer-wise reconstruction. So you only need to work on only one matrix multiplication to minimize the change of that matrix multiplication. For example, right here, we have a activation times the weight. The activation has batch size of 2, and 4 input channels. The weight has 4 input channels and 8 output channels. And we get an output tensor of batch size times CO. Okay. And then we try to prune some of the channels on the weight. For example, here we try to prune the second channel on the weight. Okay, so what is multiplied with the second channel? Actually, that's the second channel of the activation. With the multiplication, they will correspond to each other. So what is the dimension of the output after doing such channel pruning? It's the same. It's still batch size by CO, okay, because we are pruning in the CI dimension. So the batch size and CO, those two dimensions are not impacted. So although it's just a matrix multiplication, but if you want to see the pruning of large language model, basically everything boils down to matrix multiplication. So this can be quite crucial. And now we try to minimize the error between the unpruned output tensor versus the pruned output tensor. Okay, that makes the optimization local and a lot easier compared to you backpropagate across the entire all the layers and supervise it in that way. So how do we do pruning here? We can view this matrix multiplication into 4 parts. 4 is the CI dimension. Okay, so CI dimension, CI has 4, is 4. So 4 input channels, and we color them in 4 different colors. Okay, so x0 multiplied with w0, x1 minus x1 will multiply with w1, x2 will multiply with w2. Okay, so that's the corresponding activation and corresponding weight channel. So we can view them as the outer product, okay, the outer product of xc times wc, okay, and sum them together. Okay, in this case, we have 4 terms. Okay, 1, 2, 3, 4, 4 terms to sum together, the outer product. And then we apply a scaling factor to each outer product, the beta c, which is the scaling factor for each outer product. We sum them up. We try to minimize the difference between the original z and the pruned z, such that subject to we want to minimize the zero norm of beta to have to make beta as close to 0 as possible. If beta is 0, what does it mean? It means this outer product doesn't exist. This outer product doesn't exist, like this channel. Okay, so it means the channel is pruned. So how many betas do we have in this example? We have 4, right? 4 colors, we have 4 betas. If we prune in this way, means beta, the first beta. So beta 1, beta 0, beta 1, beta 3, 2, beta 3 means beta 1 is 0, okay? Corresponding to the white region that is pruned. And how do we solve that problem? So we can first fix W and then solve beta to select the pruned channel. And then we can fix beta to solve for W to minimize the reconstruction error. So we can do this way iteratively. Okay, we'll first fix W to find among these 4 beta, these 4 outer products, which outer product, if we remove them, will have the minimum impact on the output. And after selecting that beta, for example, after selecting the second channel to be pruned, we can solve W to minimize the reconstruction error, and we can do such process iteratively. Now, this could be quite helpful for pruning large language models where it's super expensive to backpropagate all the way to the very end and backpropagate to the very beginning. All right, so far we talked about what is pruning, granularities of pruning, criteria to select the weights to prune, and we're going to show a demo to strengthen our understanding of pruning. So let's now switch gear to the pruning demo. All right, this is the notebook I prepared. Let's maximize the notebook. Make the font size a bit larger so that we can see it. Okay, so in this demo, we prepared a MNIST data set to prune the network to classify the handwritten digits from 0 to 9. Okay, so if you random guess, the accuracy should be 10%. So let's run the IPython notebook, start from the beginning. Let's first do the setup. This is using Google Colab, the same infrastructure we are going to use for our homeworks. So for the free version, currently you can have this T4 GPU, which is a not super advanced GPU, but it should be enough for learning purpose, should be enough for this lecture. We run the setup and we prepare the neural network model. And then let's visualize the images. Now we have 10 digits to classify. And then we are going to retrain the neural network on the MNIST data set. And this training has started remotely in Google Cloud. And this is now running on the T4 GPU. Okay, currently about one epoch has completed. The accuracy is already 98% right here. So we are going to repeat the training process, training for 5 epochs. This is epoch 1. Actually, epoch 2 already finished, 98.6% accuracy. You can, of course, upgrade to a better GPU by using the paid version. But I think the paid version is also enough for our labs. Actually, from lab 1 to lab 4, we are all going to use Google Colab. Probably lab 4 will be a bit slower since we are going to run large language model. And lab 5 will be written in C++. So make sure you have those prerequisites to manipulate the pointers, deal with multi-threading, etc. Okay, it's the last epoch. We are already 98.9%. This is the last epoch has finished. We got 98.99%, which is actually pretty satisfying. Okay, let's first evaluate the accuracy and model size of this dense model before pruning. 98.99%, almost 99% accuracy. Okay, and this is the digit. The second row is the prediction. We can see in this batch of examples, they are all correct. So then let's do the pruning. Apply a pruning ratio. Let's start with some moderate pruning ratio. Let's maybe start with 70%. Let's prune away 70% of the parameters and see what happens. The accuracy dropped as expected, right? The accuracy dropped from 99% to 94.6%. Okay, and if you see the visualization, some of them are classified not correctly, like from 8 to 9 is a mistake. So what can we do about it? Let's fine-tune the pruned model to get a higher accuracy. And we fine-tune for 2 epochs in this case. And here's the entire code to do that. Learning rate, the momentum, the weight decay. Let's just fine-tune the model to see if we can recover the accuracy from 94% back to 99%. 1 epoch already finished. It increased to 98.78%, which is a good starting point. Let's fine-tune for another epoch. The accuracy recovered to 98 98.85%, already quite close to 98.99%. And we already prune away 70% of the parameters, only with 30% of the parameters left. Okay, so what shall we do? Let's visualize them. Let's load the model. And for these 10 examples, they are actually all correct. We're showing that by pruning and retraining the remaining models, we can pretty much recover the accuracy loss from 94% back to 98%. So let's do something more aggressive rather than pruning away 70%. Let's do 90%. Unfortunately, the model accuracy dropped to only 20%. 20%. This as expected, right? Because we are already pruning away 90% of the parameters. It's very natural the accuracy will drop a lot. For example, it's 4 that gets classified as 3. Let's see how this fine-tuning can help recover the accuracy. So let's fine-tune the pruned model to get a higher accuracy. Let's fine-tune it using the same schedule for 2 epochs. And of course, feel free to adjust the learning rate and also the momentum and also the rate decay or increasing the number of epochs to see if we can have a better result in practice. Okay, 2 epochs finished, 98.3%. Isn't that amazing? We prune away 90% of the parameters. After retraining, we can still get 98% of accuracy. So let's load the model again, classify the 10 digits. Actually, all these cases are correct. And the test accuracy is 98.35%. How about let's do something more aggressive? Someone can tell me a number you want to try? 99%. Okay, 99%. Only 1% of the parameters is left. It's very aggressive. All right, 10%. It's random guess, right? You have 10 digits, you have 10% accuracy, so that's basically random guess. Everything is 2. Yeah, someone already recognized everything is predicted as 2 after pruning away 99% of the parameters. So let's fine-tune that for epochs and 2 epochs and see what happens. And we increase it a little bit. Oh, the first epoch give you 9% of accuracy back. Okay, second one finished, 33%. So let's run the demo again. Okay, like this one is correctly predicted, and unfortunately the remaining one is not correctly predicted, right? So that's where it's pretty much the limit. 99% will not work. As you can see, we exactly played the entire curve from 70%, 90%, 99%. Even with retraining, we can recover the accuracy up to 90%. But if you prune too aggressively, like 99%, the accuracy is going to drop very aggressively and even cannot be recovered from retraining. But the technology is improving very rapidly. Maybe some of you come up with new algorithms to push the frontier, even more aggressive pruning ratio and even higher accuracy. So we have a lab for lab 1. We are going to release on next Tuesday. So you can play with the such pruning and retraining process to figure out a good training schedule. Question? Oh, the question is, what is the difference between the initial training versus the fine tuning? Okay, so the fine tuning we train for 2 epochs, and learning rate 0.1, momentum 0.9, and rate decay E-4. And we go to see the original training process. The learning rate is larger, right? The learning rate is 1, but in the training process, we reduce it by 10x. Since it's pretty much converged, so we reduce the learning rate. And initial training has 5 epochs, and the fine-tuning took only 2 epochs. Yeah, right. A question? Yeah, so training a smaller model from scratch, even train for a longer time, is usually practically worse than pruning a larger model. So during the optimization, usually redundancy is helpful for you to get away from the local minimum. For example, you have a saddle point, and then you add another dimension. If you get stuck in the local minimum, if you add another dimension, if it is saddle structure, you can go even lower. So over parameterization helps with optimization. And after the optimization, you can prune them away. Question?
When trying to remove a row or column from the matrix product, can you replace that with the truncated SVD?
When removing a row and the column from the matrix, can you?
All of the matrix and the row from others, so that the product doesn't change that much. We could replace this whole process with the truncated SVD.
So those are orthogonal techniques, SVD versus pruning. You can also prune on top of a SVD matrix. So pruning, SVD, low rank approximation, quantization, distillation, they are different orthogonal techniques to apply here. All right, so in the next lecture, we are going to cover a few techniques in next Tuesday from how to find the pruning ratio for each layer. We find that super crucial compared with uniform pruning ratio, and how to train fine-tune a prune layer and automated ways to find the pruning ratios rather than manually find them, and also how to the system and hardware support for different granularities. Together with Lab 1 will be out by next Tuesday. Actually, we already have all the labs available online. So if you're eager to try what we have tested today, feel free to grab Lab 1 from our course website, which is EfficientML.ai. And here are the references for today, which conclude today's lecture. Thank you.